Hello, my name is Eddie, and this is EC3300 Lab number 4 for Group C. In this lab, we are asked to have a BCD counter that only uses the first 7-segment display and the very last 7-segment display, as well as an input switch and a reset button, where the input switch will begin the counter if it is turned on or high, and if it is turned off or low, the counter will stop counting and keep the same number it was currently at. If the reset button is pushed, then both 7-segment displays will be reset to 0. And here's our code. So first we set an input called mClock, where the clock frequency is the default 100 MHz, and we have an input called enable that will act as our input switch, and we also have a reset input that will reset the values to 0. And here we have outputs dp, which is the decimal point in the 7-segment display that we set to have always turned off. And our output A2G is the output for the 7-segment display, and output AN is the anode selector that will determine which 7-segment display will be turned on or off. Since our default clock is 100 MHz, we needed to slow down the clock because 100 MHz is too fast for our 7-segment display. So in order to do this, we have to make a clock divider so that the 7-segment display has enough time to display the number. So here we set the local parameter post value change equal to 50 mil. This parameter will make sure that we have a clock signal that is 1 Hz, which means that we would get a counter that increases every second. And here we have a 26-bit register called numCount, and we set that equal to 0. It needed to be bigger than 50 mil, and 2 to the power of 26 is approximately 67 mil. Here we set a register called clock level. And here is the always block that increases the counter num count when the clock rising edge arrives. And this always block is basically a clock divider that provides a 1 Hz clock signal, meaning our counter on the FPGA board will increase every second. So here we check if 50 million clock cycles have passed. If it doesn't, then we increase the clock cycle by 1, and we keep the clock level the same. And if 50 million clock cycles have been counted, then we restart the cycle count and we invert the clock level. And here we set the refresh clock counter. We named the register refresh count and set it equal to 17 bits. This 17 bits gives us a 2k Hz refresh rate, and when we reach the clock's rising edge, we increase the refresh counter by 1. Next, we began the counter for each display, as well as the enable switch and the reset button. So here we named 2 registers called LSD BCD, which is the least significant digit or the display on the very far right, and the other register is called MSD BCD, which is called the most significant digit or the 7-segment display on the very far left. So at the rising edge of the clock, we begin this always block. So first we check if the enable switch is high and if the reset button is not pressed. If that's true, then we move on to this next part where we check if the display on the far right is equal to 9. If it is, then we set that digit to 0. If it is not, then we increment that digit by 1. And here we then move on to checking the most significant BCD, or the display on the far left. If that is equal to 9, then we set that digit to 0. If it's not equal to 9, then we increment that value by 1. And here, if the reset button is pushed, then both display values are set equal to 0. And here we are refreshing the 7-segment display. We named a 4-bit register BCD num to store either the digit on the far right or the digit on the far left. And whenever refresh count LSD BCD or MSD BCD is changed, we check to determine which 7-segment display we need to refresh or update that number. So we check the 15-bit of refresh count, and if it is 0, then we display the value on the 7-segment display on the far right. If it is 1, then we display the value on the 7-segment display on the far left, or the most significant digit. And we set the default case to the least significant digit, or to the display on the far right. This next always block will determine which number is being shown on the 7-segment display. It basically decodes the outputted number based on the refresh segment above. If the BCD number is 0, then we display 0 in the 7-segment display using the cathodes, and A2G is used for that. And we also set the default value, or the default output, to be 0. And here on our XDC file, where you can see that we have our input clock here, and we set the first switch to the enable switch to turn on the counter, or to pause the counter by turning it to low. And here we set our A2G values, which determine which segment in the 7-segment display is to be turned on. And here we set the decimal point value here, but earlier we set it equal to once, which will keep it always turned off. And here is our anode values that will tell us which 7-segment display will be turned on, or these values here. And then we have our reset button, which I set it to BTNC, which is basically the middle button on the FPGA board on the far right. And that is it for my part.
The display selector. So to start, we have 0 on both of our displays. That's why we see this large green block. We're alternating between 7-segment displays for every value. So at the start, for the first second, we see enable is low, and then at 1 it spikes up. And we see at half a second that we get a change in value right on over here, and we can see that it goes from 0, 0 to 0, 1. So this is the lower display, and then this is our upper display. And then we have a reset, but since our reset is tied to the always block that we have, that is with the clock divided signal, our reset takes at least, or I guess at most, half a second of being pushed down in order to actually reset the values in our 7-segment display. So if we zoom in over here, we'll see at 2.5 seconds that it does indeed reset the value. When we go down over here from enable being high to low and reset is low, we'll have a value of 4, so 0, 4. And then as it's being held low, we can see that the value stays constant. And then now when we go back to when enable goes high, we can see that our value is still the same once enable is high. And then we can see later on, say at like around 11.5, we'll see a change in value because our counter is counting up. So we'll see over here that it's a 0 on the upper display and 6 on the lower display. And then we can see that that ends up changing to 0 on the upper display and then 7 on the lower display. Due to my computer's low amount of memory, I wasn't able to simulate a rollover, so I'll do a part 2 to that and show the rollover from 9 to 0 on the lower display, and then also 99 to 00. Okay, so now this is going to be part 2 where we see the rollover happen in our 7-segment displays. So you can see here that I modified my test bench a little bit. So I have enable on to start, just so that way I didn't have to use as much RAM because these test benches are taking a while to load. So after 2 seconds I let it finish, and then I modified our existing code a little bit. So to start, I made sure that the lower or least significant digit start with 9 on our 7-segment display, so then that way I didn't have to cycle through all the values. So we can see here at the start that enable is high, and actually let me zoom in a little bit. Anywhere over here is fine. We can see that we have 0 on our upper segment, and we have 9 on our lower segment. And actually we can see later down the line at around 1.5 seconds or so that we see 11 on both of our displays. If I zoom even in a little bit more, you can see that it's going to both displays. So the rollover does happen successfully. I'll even try to zoom in over here around 1 second or so. So yeah, this is just around 1 second. We could see that on our lower display we have 0, and then on our upper display we have 1. So I'll have a part 3 that shows the rollover from 99 to 00. Okay, so this is the last part of the test bench. Once again, I changed the code just so that way I didn't have to loop through every single value to see the rollover from 99 to 0. So we can see here the least significant and most significant digit both have a 9 to start with. And my test bench used the same one as last time, and we can see here that both 7-segment displays are showing 9, and then after about half a second or so, they both change to 00, which is what we want. So that shows that our device is working properly.
This is our demo for Lab 4, in which we had to program a 7-segment to perform an up counter. So first we can see that this digit right here is our least significant bit. This is our most significant bit. And right now it's off, the enable is off right here. And when I switch it on, it'll start counting. And when I switch it off, it should stay on the current digit. And then when I switch it back on, it just continues counting. So this digit right here will increment each time this digit will reach 9. And we also have our reset button right here. When I press it, it'll just reset it back to 0. Or reset it again.